Hello everyone, welcome to my channel. So now we have a question which says the correct set of possible term symbols for the electronic configuration 1s2, 2s1, 2p1 is. So we have to identify the term symbols among these four options for this electronic configuration. Now looking at the electronic configuration, we very well know that the inner electrons do not contribute to the term symbols because they have their L and S is equal to 0. So they do not contribute to the J value. And without these values, we cannot write the term symbols. So we avoid this 1s2 and that means we have to find the term symbols for only these two, 2s1 and 2p1 electronic configurations. So we have to consider only 2s1 and 2p1. Okay, now for 2s1, the principal quantum number is 2, we know that. Then the azimuthal quantum number L1, let us say it is L1 for this part, the S part, 2s1. So L1 comes out to be 0, okay, since we have 2s. So that comes out to be L1 equal to 0. Okay, now what about the spin quantum number? So the spin quantum number, so we have only one electron. So let us say this is S1, which is equal to half. Okay, only one singly occupied electron in the 2s orbital. Now for 2p1. Okay, so for 2p1, n equal to 2. What about azimuthal quantum number? L1 is equal to 1. Yes, for p. So we have L1 equal to 1 for p orbital, and then again in this orbital also we have one electron, so the spin quantum number becomes only half. Okay, so this is S2, sorry, so S2, and let us say this is L2. Next we calculate the total orbital angular momentum quantum number, and this we know is the summation of the azimuthal quantum numbers L1 plus L2. We have two azimuthal quantum numbers here. So the total orbital angular momentum quantum number becomes L1 plus L2 to L1 minus L2. Okay, so total orbital angular momentum quantum number is indicated by capital L. So L1 is 0 and L2 is 1. Okay, so 0 plus 1 to 0 minus 1. That is equal to only one value we have, 1. Okay, that is because the total orbital angular momentum quantum number cannot be minus 1. We have from here we see that we have 1 and minus 1 values, but since capital L, this total orbital angular momentum quantum number cannot be minus 1, it can have values either positive or 0. So we have only one value of L here, capital L here, that is 1. Okay, now from here we can very well identify our base terms. So we have L equal to 1, and we know for L equal to 1 we have the term symbol, or you can say the base term is P. Okay, if you remember, so we have 0, 1, 2, 3, 4, 5 like that numbers which correspond to L, and the corresponding base term or the term symbol is S, P, D, F, G, H and so on for the corresponding orbital angular momentum quantum numbers. So if you remember this, so L equal to 1 belongs to the term symbol of P. So the base term becomes P. Now we calculate the total spin angular momentum quantum number. So total spin we calculate now. So that also is S1 plus S2 to S1 minus S2. So S1 and S2, here we can see S1 is half, S2 is half. So half plus half to half minus half. Okay, that comes out to be 1 and 0. The S value comes out to be 1 and 0. Next we calculate the spin multiplicity. So we will calculate multiplicity from our spin quantum number. Okay, so we have two values for our spin quantum numbers. So that is for S is equal to 1. We have 2S plus 1 is equal to 3. That is a triplet. And corresponding to that, the term symbol becomes, we have the base term P, multiplicity is the superscript, we know that. So like this, 3P, okay, or P3 or 3P. Now for another s value, for s is equal to 0, we have two values for s here. So for s is equal to 1, we have multiplicity is equal to 3 or triplet. Base terms comes out to be P3. Okay. Then for s is equal to 0, we have 2s plus 1 is equal to 1. That is a singlet. So the term can be written as 1p. Okay. Like this. Now after this, we finally calculate the possible j values. And we know very well that j can be calculated like this: L plus S. It has a value ranging from L plus S to L minus S. Okay, so we calculate for P3 how many j values we can have. So for P3 we have L equal to 1, S is equal to 1. So we can have L plus S, 1 plus 1 to 1 minus 1, that is equal to from 2 to 0, 2, 1, 0. So these three values will be there for the P3 term symbol. The j values for P3 symbol will be from 2 to 0, 2, 1, 0. It will have three values. Okay, now for P1 or 1p, what we have for 1p, we have L equal to 1 and S is equal to 0. So what we have 1 plus 0 to 1 minus 0. That means we have only one value, that is equal to 1. So j is equal to 1. So this is the j value for 3p or s is equal to 1, and this is the j value for 1p or s is equal to 0. So you have to understand carefully that what we are doing. So we have the final j value for two spin quantum numbers. S is equal to 1. We have two 1, 0 j values, and for s is equal to 0, we have only one j value, that is 1. Okay, now we have the superscript ready with us. So we have the multiplicity 3 and 1. So we have written 3p and 1p. And now we have to put the j values as the subscript, that we know how we write the term symbols. So superscript is our multiplicity and subscript is our j value. So 3p2, then 3p1, then 3p0 for s is equal to 1. So we have three possible term symbols for s is equal to 1. 3p2, 3p1 and 3p0. Now what about s is equal to 0? We have only one possible term symbol, that is 1p1. So these are the total possible term symbols for the electronic configuration of 2s1 and 2p1. So these are the possible term symbols. So I hope you understood what we did here. First of all, we came to a conclusion that the inner shells will not be accounted because there is no contribution to the j value, because L and S for the completely filled inner shell is 0. So that we will not take into account while writing the term symbols. Then 2s1 and 2p1. So remaining 2s1 and 2p1 we take into consideration for writing the term symbols. So we calculate the azimuthal quantum numbers for each of these 2s and 2s1 and 2p1 configurations. Then we find out the spin quantum numbers. Then from the individual azimuthal quantum numbers, we find out the total orbital angular momentum quantum numbers. And then from here, when we get the total orbital angular momentum quantum number, we get the base term p. Okay, and then we get our total spin values as 1 and 0 from the individual spin values. Okay. Then after getting the total orbital angular momentum quantum number, we acquire the base term, and then after we have the spin angular momentum quantum number from the two spin values of the two configurations 2s1 and 2p1, and then we calculate the spin multiplicity. So we have different spin multiplicity for these two different spin quantum number values. So we have triplet and singlet, and from here we assign the term symbol with the superscript of the multiplicity. Okay. And lastly, what we calculate? Lastly, we calculate the j values from L plus S to L minus S for each of the spin quantum number values. Because we have, for L, we have only one value, 1, 1. Okay. So we have different spin values, and from different spin values, we have got different J values as well. So for 3p or S is equal to 1, we have 3 J values, 2, 1, 0. And from 1p, that is S is equal to 0, we have only 1 J values, that is 1. And then we combine these terms with the superscript. We have a total of 4 term symbols arising from the 3 term symbols corresponding to multiplicity of 3 and the J values of 2, 1, 0. And lastly, we have J value corresponding to 1. So this is how we have a total of 3 plus 1, that is 4 term symbols for 2s1 and 2p1 electronic configuration. Okay, now let's move back to the question. So let us check what all options we have. For P3, we have 2, 0, 1 values, and for P1, we have only 1 value, 1 P1. So option 4 is our correct answer for this question, and I hope this explanation was clear to you. And if you like my videos, please like, share and subscribe, and please let me know your problems in chemistry in the comment section. Thank you so much.